What's up, everybody? Welcome to lecture 7, which is all over section 1.8. Today's lecture is just going to be about a bunch of theorems, their implications, as well as some definitions. I'm not going to go over any examples in this particular lecture video, and that's because I want y'all to go back to your notes and to dig through those example problems on your own. The reason for that is that honestly, these are some good problems for making sure you understand how limits work. And just to make sure you have some of the intuitive understandings that you need. And if I just present all of these problems on the board in the lecture video, well, there's no guarantee that you actually understand them, right? You might follow along and be like, yeah, well, obviously. But if you go back through your notes and you look at a problem, you say, I don't know how to solve this one, you'll know that there's a reason for that. You'll know that that means, okay, when I was following along in problems in past videos, it made sense because it was being presented to me, not because I understood it. And there is a distinction there. It's something that, like I said, should be challenged. Having said that, let's get into this lecture. So this lecture is all about continuous functions and what it means for a function to be continuous, as well as some implications that occur in the face of continuity. So in order for a function to be continuous at a, then we need that the limit as x approaches a of f of x to be equal to f at a. Now, we have this intuitive understanding graphically that continuity would mean you can draw the graph without picking up the pen. I mean, for the most part, yeah, that's what that's saying. But notice there are 3 different requirements within this definition. The first requirement is that the limit exists. The second requirement is that your function exists at a. And then the third requirement is that the limit is equal to the value of the function. Now, in the notes, there is a collection, or there is a graph, which shows the different types of failures that occur, or the different types of continuity, or discontinuities rather, that occur when each of these fail. So when this fails, it has a particular type of discontinuity. When this fails, it's a particular type of discontinuity. And when this fails, it's a particular type of discontinuity. So something to look at would be, again, these 1.8 notes. Having said that, we have this idea of continuity from directions, right? Continuity from the left and from the right. And just based off of this, you might be able to guess what the definition for continuity from the left and continuity from the right will be. So if you're continuous from the left, then it means the limit as x approaches a from the left of your function f of x is going to be equal to f at a. And similarly, from the right, you need that the limit as x approaches a from the right. So, some slight distinctions there, nothing major though. Notice though, this idea of continuity, it's going to require us to talk about a whole bunch of numbers all at once. It doesn't make sense to say, I'm continuous at 1 and count every value until you get to the end of that interval, right? Like that's just not, you can't do it. It's impossible to do. So oftentimes when talking about continuity and discontinuity, it's easier to talk about where you're discontinuous than it is to talk about where you're continuous. So you could, instead of saying I'm continuous from negative infinity to 1 and 1 to infinity, you could say I have a function that is discontinuous at 1. So it says the exact same thing, just the other way around, right? Having said that, check out some implications in other theorems involving continuity. Some other details that we should be aware of when talking about continuous functions are the way continuous functions relate to one another in terms of addition, multiplication, etc., etc., etc. So if A and G are continuous at a point A, then so are the sum and difference of f and g, the product of f and g, the quotient of f and g so long as g is equal to 0, and so is a constant multiple of f. So if you're continuous at a point, all of those will also be continuous at that point. Meanwhile, there's two particular functions that we like to work with a lot, polynomials and rational functions. And I've written up here when they're continuous, but I think it would be better off for me just to tell you what functions are continuous everywhere in their domain. Those functions are polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. Yeah, I'm reading that right off the slide, but only because I'm definitely going to forget one of those if I didn't have that slide with me, right? But what this means is that each of these functions, as long as the function gives you a value, it's going to be continuous at that value. In other words, any value that one of those functions spits out a number or is defined, well, it's continuous then. Those functions are only discontinuous at the places that they are not defined. That's what that list is on. Of the functions that are discontinuous only at the places that are not in their domain, or another way of saying that, at the places where they are not defined. Having said that, let's keep chugging along. Alright, so for this last little bit of the lecture, we're just going to go over these three different theorems. First, if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is equal to the limit of, my mistake, is equal to f of the limit as x approaches a of g of x. In other words, you can just pass that limit inside. On the other hand, if g is continuous and f is continuous at g of a, so if g is continuous at a, and if f is continuous at g of a, then so is their composition. So in other words, if you take two functions that are continuous and compose them together, you get a continuous function. And finally, we have what's called the intermediate value theorem. If f is continuous inside of some interval, then for n between f of a and f of b, there exists a c inside what's called the open interval from a to b, such that f at c is equal to n. In other words, take any collection of number from a to b. You're including a to b. You want to know what the function is on the extremes, right? So you need to know what f of a is, you need to know what f of b is. Now, between f of a and between f of b, you're going to take a number, call it n. You're going to pull that out, set it off to the side. And then you're going to come back to that first interval. And you're saying, well, there's a number between a and b, not including a and b, that we're going to call c. And this c, it just sits somewhere in between a and b, but it has a special property. It has the property that your function evaluated at it is equal to n. That's all it means. In other words, if your function is continuous at that interval, you can always find a number in that interval that will spit out a value between the endpoints of that interval. That's all I'm saying. Whereas these other two are just getting at the way continuity works when you pass functions through each other. This one is saying that if f is continuous, it is continuous at g of a, and if g is continuous at a, then the limit, or my mistake, then the composition of the two functions are continuous at a. And this first one, again, is just saying that there's a method by which you can pass the limit into the composition of two functions. So if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then we pass that limit aside. Having said that, that is all I have for y'all. Again, I would like y'all to go through those notes and look at them. Obviously, I've left out doing example problems in this lecture. It's just simply because I wanted y'all to go back through those notes and look at them yourselves. I believe that this particular section does a pretty good job of helping you check whether or not you understand the material. That said, if y'all have any questions, by all means, please shoot me an email. As of right now, I have not decided on my office hours yet. I will be posting that as soon as I know, which I anticipate being Monday. What else do I want to say about all this? I guess that's it. Stop by office hours if you have questions or shoot me an email. Otherwise, have a good one, everyone. Cool.